Hi guys, welcome to Chemistry, Unit 3. This is about atomic structure. And I like to say that this is kind of like where chemistry truly begins. Everything up to here has been a lot of kind of physical science. In chemistry, you got to understand the atom. So let's look at atomic structure. First off, let's start off with some basics of the atom. Some of the stuff you probably nailed in middle school, so let's just go through the real quick basics of the atom. You have your proton, your neutron, and your electron. Those are your three components that make up the atom. There's smaller things in that, but we're not going to get into them in this class. You have leptons and muons and positrons and all kinds of things. But for this class, the atom is made of three things: protons, neutrons, and electrons. Protons are positive. They have a positive 1 charge. Neutrons are neutral. They have a 0 charge. And electrons are negative. They have a negative 1 charge. So protons positive, neutrons neutral, and then the only one that's kind of hard to remember, electrons, the only one left, negative. Proton positive, neutron neutral, electron negative. Where are they at in the atom? The proton and the neutron make up the central part of the atom called the nucleus. Now, if a few of you might have had biology and you know there's a nucleus in biology, don't get confused. This is completely different. Nucleus just means the center. And so in biology, nucleus has DNA and things like that, but this class is completely different. Proton and neutron are in the nucleus. That's in the center of the atom, and the electron just orbits around the nucleus. It's all over the place around the nucleus. And then finally, for mass. Well, here's something pretty cool. A lot of times in science, they make up these things that are hard to remember, but chemistry, they do things that are pretty easy sometimes. In chemists, the mass of these guys is so small, that's weight if you're talking about gravity, but the mass is how much matter you have. It's so small that scientists actually created their own unit. And if you look down here at the bottom, this is the AMU. AMU is the unit used to measure atoms, and it's pretty straightforward. Atomic mass unit. Thank you, chemists, for hooking us up with that. And AMU is a measurement of atomic mass. So they made it pretty simple, and they just made it so a proton weighed 1 AMU, has a mass of 1 AMU. The neutron has a mass pretty close to that of 1 AMU. That's what these little squiggly lines are mean about. And here's where it gets kind of interesting. The electron's mass is so small that it's approaching 0. Now, it still has mass, and it's made of matter, but since it's so incredibly small and so much smaller than the proton and the neutron, for our purposes, the mass of the electron is pretty much 0. So let's look at some other things. This is what you see off of the periodic table here. This is a little slice off the periodic table. And up here on the top of the periodic table is your atomic number. Atomic number is your number of protons. That tells you the identity of what you're talking about. Your atomic number can never change. If this is neon, neon has 10 protons. If neon had 11 protons, it wouldn't be neon. If it had 9 protons, it wouldn't be neon. How many protons you have tells you what you are. Neon, 10 protons, it's what it is. It determines the identity of the atom. Down here, you have the atomic mass. We'll get to that in a little bit. But not on the periodic table, we have a mass number. Mass number is just how much mass you had. Now, on the previous slide, we just said that protons and neutrons have 1 atomic mass unit, and electrons are almost 0. Since electrons are almost 0, then the mass number is your number of protons plus your number of neutrons. This number is not on the table, like I said. So for neon, there is no mass number up here, but this is the atomic mass, so let's average it out, and let's say the mass number was 20. If the mass number was 20, that means you got 10 protons. 20 is your total, so 10 plus what equals 20? You'd have 10 neutrons. So like I said, we'll talk more about that a little bit later. And then the final thing you can talk about with an atom is its charge. Now you think back to the previous page. Protons were positive, neutrons were neutral, electrons were negative. So to find charge, you're going to worry about the protons and the electrons. You're not going to care about the neutrons because neutrons are 0. And what happens when you add or subtract zeros? Nothing. You have nothing there. So to find the charge, you consider the number of protons and the number of electrons. We'll talk more about that later as well. If something's charged, you call it an ion. An ion is any atom that has a charge. These can either be called anions or cations. I know that looks like anion and cation, but trust me, anion, cation. Anions are negative, cations are positive. For anions, you have more electrons than protons. Now, I just told you can't change the number of protons, so how that happens is you have to, well, let's skip over here first. For cations, you have more protons than electrons, but like I said, you cannot change the number of protons that you have. So to become an anion, you have to gain electrons. To become a cation, you want more protons, so you have to lose electrons. You cannot change protons. Cannot change protons. You can gain electrons. You can lose electrons. This is what happens when you shuffle your feet across the floor. You're moving electrons back and forth, and when you touch somebody, that causes more electrons moving back and forth. That's what shocks them. So you can gain and lose electrons. You cannot change the number of protons. Here's a good way to remember anion and cation. So I think that anions are negative ions. Anions are negative ions. A-N-I, are negative ions. And then when you look at a cation, you can see a positive ion. See? C-A positive. T. Cation. C-A positive. And if you like cats, you can just remember cats are positive, but if you don't like cats, that doesn't really help you there very much. So when I say a cation, I see a positive ion. Anions are negative ions. So let's fill out a chart here. So we have description on the left, and we have our net charge, atomic number, mass number, and ion symbol. So we have, actually I take it back. Let's do this in class. Okay, we'll talk about this more in class. So I'm going to fly past this. We'll talk about that more in class. Let's talk about isotopes. Isotopes have different varieties of an element's atoms. So to be an isotope, you have a different mass, which means you have a different number of neutrons. Now, why not different number of protons? Well, because you can't change the number of protons. We just said that. So isotopes have different number of neutrons, thus they have a different mass. Some isotopes are radioactive. You might have heard that before, like a radioactive isotope. Others aren't. So let's look at an example here. For hydrogen 1, anytime you have a number here, that's telling you the mass. So for hydrogen 1, its mass is 1. For hydrogen 2, its mass is 2. It's for hydrogen 3, its mass is 3. Oh yeah, and it doesn't really matter what an isotope is because it's still going to react the same chemically. And we'll talk more about that later. So hydrogen 1 has a mass of 1, hydrogen 2 has a mass of 2, hydrogen 3 has a mass of 3. Okay, so hydrogen 1 is number 1 on the periodic table. How many protons? 1. How many for hydrogen 2? 1. How many for hydrogen 3? 1. Because you cannot change the number of protons. How many for hydrogen hanging upside down by its toes? 1. How many for hydrogen on Thursdays? 1. Doesn't matter. Number of protons is who you are. So now let's look at the number of neutrons. Remember we said mass is protons plus neutrons. So this is a pretty easy math problem. 1 plus what equals 1? Hopefully everybody yelled 0. Now for this one. 1 plus what equals 2? Pretty easy. 1. 1 plus what equals 3? 2. So you can find your number of neutrons if I ever tell you the mass of something, because all you're going to do is take the mass and subtract it from the number of protons. You get the number of neutrons. Okay. Common name for these guys, don't really need to know. If I have anybody tries out for Quiz Bowl, that is a common Quiz Bowl question, but we're never going to ask you about protium, deuterium, and tritium. So let's look down here at carbon 12 and carbon 14. Hopefully you have your periodic table that you're looking on with here, because I want you to look at your periodic table and tell me how many protons that these guys have. All right. So you should have come up with 6 because it's number 6 on the periodic table. And for carbon 12, 6 plus what equals 12? 6. And carbon 14, you still have 6 because it's still carbon. 14 atoms. You need 8 neutrons to get there. Carbon-12 is stable. You're made of mostly carbon-12. And carbon-14, you have a little bit of carbon-14 in you that starts to decay as soon as you die, and that is radioactive. That's how you tell how old bones are and things like that. So real quick on radioactive isotopes, all nuclei want to not be radioactive. They want to be in that stable form. So like carbon-12 is happy, carbon-14 is not. So carbon-14 wants to decay to get to a more stable form. You don't really need to understand why. We'll talk about that later. So nucleus attempts to attain a lower energy state, so it releases energy. That energy is released as radiation. You might have heard of radiation before, things like nuclear power and nuclear bombs, things like that. But that radiation energy is energy that's either in alpha particles, beta particles, or gamma rays. We'll talk more about that a little bit later on as well. Half-life is just the fact that these guys are going to decay at a constant rate. So what you can do is you can look at carbon-14. Its half-life is 5,730 years. So it's really good at measuring human fossils because you can see how old it is depending on how much carbon-14 has decayed. And we'll talk about that a whole lot later on. So not really worried about the half-life and decay right now. We'll come back and talk about that later on. So let's look at complete atomic designation. Right. So here you have iodine. This is iodine written in complete atomic designation. And I'll write this a lot in class, and you're about to see an example on the notes that I'll probably skip past real quick like I did the other chart. But so your mass is always at the top left. Your atomic number is always at the bottom left. Your charge, if you have one, is always at the top right. And it doesn't matter whether you put the negative in front or behind. If you see in class, I'll usually write the negative on the left-hand side just because that's what we do in math class, and that makes our life a whole lot easier. Anything, and there's a couple pictures here about iodine. Iodine is in your diet, and we need iodine for our thyroid to work properly. If you don't have it, you keep telling your thyroid to work properly, and you end up with goiter because you don't have lack of iodine. Our salt, most of it is iodized salt, which gives us iodine for free, and we don't end up with a goiter. Like I said, I'm going to skip past this slide because we are going to do something very similar to that in class. So let's talk about some history. The historical development of the atomic model. First off, you start with these Greeks, very similar to they did in the very first chapter we did, where you had the Greeks with Aristotle with the elements. But the Greek model started with Democritus and Leucippus. And actually, I'm going to stop there. So I'm going to stop this video.